Using the Logit and Probit models, we can make predictions about the probability of success or the probability that the dependent variable is equal to 1. In our example, we can predict whether an individual will purchase a car or not, given the age, income, and gender of that individual. We can use those probability predictions to assess how well our model is performing with the help of a classification table. A classification table shows us the number of correct predictions as well as the incorrect predictions made by our model. To construct a classification table, we have to choose a cutoff value for classifying the observations. Usually, we use a 0.5 cutoff. If the predicted probability is less than 0.5, then we predict that the individual will not purchase a car. On the other hand, if the predicted probability is equal to or greater than 0.5, then we predict that the individual will purchase a car. This way, we can label each observation as 0 or 1 using the predictions, where 1 means that the individual will purchase a car. Finally, we compare the predicted labels with the actual labels or data that we have for the dependent variable. In practice, a classification table will look like the one shown here. The columns of the classification table here represent the true values and the rows represent the predicted or classified values. The first element of this table shows the true positives. That is, it shows the number of observations that purchased a car, and our model also predicted that the individuals will purchase a car. Therefore, the dependent variable x was 1 in the data and our model also predicted x equals 1. The fourth element of the table shows the true negatives, which are the number of observations that did not purchase a car, and our model also predicted the same. Hence, the dependent variable x was 0 in the data and our model also predicted x equals 0 correctly. These first and fourth elements, therefore, show the total number of correct predictions made by our model. The second element in the table represents the false positives. These are the number of observations where the individuals did not purchase a car, but our model incorrectly predicted that the individuals will purchase a car. Finally, the third element shows the false negatives. These show the number of observations where the individuals purchased a car, but our model incorrectly predicted that they will not purchase a car. Therefore, the second and third elements show the number of incorrect predictions made by our model. Earlier, we discussed a 0.5 probability cutoff to make the predictions. This will not always be the best choice, so we can choose a different cutoff based on our research objectives. For example, let us say that we have a model where we want to predict the probability of default on a loan. Our objective may be to recognize individuals who are more likely to default on a loan. If we don't want to miss any possible defaulters and decrease the false negatives, we can lower our cutoff to say 0.3 instead of 0.5. This will lower our false negatives because we have chosen a lower probability cutoff. Any individual with a probability higher than 0.3 will be predicted as a defaulter. On the other hand, this may increase our false positives because some individuals might be incorrectly classified as defaulters due to a lower cutoff. Let us continue with our example of the decision to purchase a car and estimate the classification table for the Logit model. First, we have to predict the probability of purchasing a car for all the observations or individuals in our sample. It is important to note here that we can also do this for out-of-sample observations. For illustration, we will use in-sample observations here. The predict functions in our data can be used to predict the probability of success or probability of purchasing a car for all observations as shown here. From these predicted probabilities, we can construct a classification table after the Logit model. The commands shown here can be used to construct the classification table. In R, we are using the round function to round off the predicted probabilities to 0 or 1. This means that we have automatically chosen a 0.5 cutoff for classification. In Stata, 0.5 is the default cutoff, so we don't need to mention it in the command. The results of the classification table after Logit model with a 0.5 cutoff are shown in the table. Out of our sample of 1,000 observations, we have 297 true positives. That is, 297 observations were correctly predicted to purchase a car. Similarly, we have 539 true negatives, that is, 539 observations were correctly predicted to not purchase a car. These diagonal elements give us the total number of correct predictions, which is 297 plus 539 and equal to 836. Therefore, our Logit model predicted 836 observations correctly out of 1,000, giving us an accuracy of 83.6%. On the other hand, we have 59 false positives and 105 false negatives. These are the incorrect predictions made by our Logit model. As we discussed earlier, we can also use a different cutoff if needed. Suppose we wish to use a 0.7 cutoff instead of 0.5. In Stata, this can be easily accomplished using the cutoff option as shown in the command. We can mention any cutoff that we want to use within this option. In R, we have to manually estimate the predictions with the cutoff using the if-else functions as shown in the commands here. The if-else function here will classify the predictions based on the 0.7 cutoff that it mentions here. It will put a label of 1 if probability is equal to or greater than 0.7 and a 0 otherwise. The results will be saved in the custom cutoff object. Then, we can construct the classification table using the custom cutoff as shown here. In our example, this does not work too well because the accuracy of our Logit model has fallen to 79.3% when we use a 0.7 cutoff as compared to 83.6% earlier. The number of false positives have reduced from 59 to 32, but the false negatives have increased from 105 to 175. Now let us compare these results of the Logit model with the Probit model. The classification table after the Probit model is estimated using the same commands. The only difference is that we input the results of the Probit model in the commands, instead of the Logit model. If we look at the classification tables from both the Logit and Probit models, we see quite similar results. The true positives in the Probit are 286 as compared to 297 in the Logit model. The true negatives are 542 in the Probit, whereas they are 539 in the Logit model. Therefore, the Probit model is doing marginally better in true negatives or identifying individuals that will not purchase a car. On the other hand, the Logit model is performing marginally better in true positives or identifying individuals that will purchase a car. The number of false positives is 56 in the Probit model, which is lower than the 59 false positives in the Logit model. Similarly, the number of false negatives is 116 in the Probit model, which is higher than 105 in the Logit model. Overall, we have 836 correct predictions out of 1,000 in the Logit model and 828 in the Probit model. Hence, in our example, the Logit model gives us a slightly better accuracy of 83.6% as compared to an accuracy of 82.8% in the Probit model. Apart from the classification table, we can calculate pseudo R-square to assess the performance of the model. The usual R-square that we estimate after the ordinary least squares is not applicable in the case of Logit and Probit models. There are many different versions of pseudo R-square that can be estimated. One of the most commonly used ones is the McFadden R-square, which is estimated using the log likelihoods of the Logit and Probit models. The formula for the McFadden R-square is shown here. The LLUR in this formula represents the log likelihood of the unrestricted model and LLR is the log likelihood of the restricted model. In our example of the decision to purchase a car, the unrestricted model will be the Logit or Probit model we estimated with all the independent variables of age, income, and gender. The restricted model will exclude all these independent variables and include only the constant. In Stata, this McFadden R-square is reported by default along with the results of the Logit and Probit models. In R, however, we have to estimate the McFadden R-square separately. We can do this using the PR2 command provided by the PSCL package as shown here. Alternatively, we can also estimate it manually using the loglit function from the stats package. The McFadden R-square can be used to compare the performance of models with different independent variables. Usually, model with a higher McFadden R-square should be preferred. In our example, this McFadden R-square is equal to 0.4487 in the Logit model when we included all the independent variables of age, income, and gender. Suppose if we included only income and removed age and gender from the Logit model, then this McFadden R-square is only 0.1026. Therefore, we know that the Logit model with age, income, and gender should perform better as compared to the model with only income as an independent variable. Thank you for watching, and I hope you liked the tutorial series.